Where does it come from? Where do we? Because natural selection, we know, requires genetic variation, right? Got to have genetic variation. Got to have over reproduction. Got to have competition. Where does the variation come from? Where do new traits come from? Mutation. Good. Source number one, kind of the ultimate source, is mutations. Absolutely. Mutations are errors in DNA replication. Mutations are errors in DNA replication. They happen. They don't happen very often. You have a whole system built to fix them. Right? You've got this whole, like, what's the name of that gene? P53, remember that in the cancer unit? Like, P53 can fix it. It can stop that cell from dividing. It can even self-destruct the cell. But every once in a while, a mutation gets through. And that's, you know, kind of thank goodness for that, because that's where new traits come from. And when you Google mutants, that's what you get.
That's fallout.
Uh-huh. I don't know if any of those are real. It's just, all I know is I did a Google image search like 3 years ago for mutant, and that's what I got. So there. But that was a ripped cow. But once you have new traits, it turns out some populations evolve faster than others, because some populations have this newfangled kind of reproduction called newfangled. I don't know. I mean, it's much more recent than asexual reproduction. Because remember, looking for two answers here.
Oh, is it the one where, like in the documentary, where like only the
No. Sex creates variation because of two things.
Oh.
And those two things are, Chris? No.
Yes.
No, I mean, there are two parents. That's great. But like, even if those two parents have 10 kids, every one of the 10 kids will be different. Why? Thank you, Jane. Crossing over an independent assortment. You should write that in. Crossing over an independent assortment in late prophase 1 and metaphase 1 of meiosis. That's the trick. You take what your parents dealt you and you shuffle it back up before you deal it out to your kids. And that greatly increases diversity and speeds up evolution. Sex, though, does not create new traits. It just takes the ones that are in the DNA and shuffles them up. Now, in doing that, it can uncover traits that weren't visible before, right? Like recessive stuff that didn't get expressed before. But it doesn't actually create new traits. That's up to mutation. All right. Back to that whole speciation thing. We remember we talked about the three different kinds of selection on polygenic populations. Directional, where it shifts the curve. Stabilizing, where it kind of just smushes it. That was the baby's example that scarred you for life. And then, what's the third one called? Yeah, disruptive selection creates the little dip in the middle at first. And if it's strong enough, it can actually make two separate populations. And if they can't or won't interbreed, we said that's two different species. That's speciation. Well, let's talk about ways that that can happen. It's not just disruptive selection that creates new species. It just takes one population becoming different enough from either a part of the population it's been split from or its ancestors say and its ancestors. Different enough, basically, that they can't or won't interbreed. So we're going to talk about a couple of mechanisms there. The word is reproductive isolation. That's the can't or won't part. When you're reproductively isolated, it means either you can't physically mate or you won't. And three subsets of that. Picture a herd of, I don't know, pick an animal that there's herds of. Herd of buffalo, buffaloing their way across the Great Plains. And suddenly, oh no, there's an earthquake and a big fault line opens up right in the middle of the buffalo. About 10 of the buffalo are not buffalo anymore. They're down at the bottom of the fault line, but the rest of them are split in two. All right, the herd of buffalo now can't get back at each other. Right, they've been split into two distinct populations. That is the beginning of what we call geographic isolation. Geographic isolation is simply, it doesn't have to be a dramatic thing like that. It can be as simple as, you know, some birds get blown off course from their main flock and now they're somewhere else and they can't get back to their original flock. Geographic isolation is just physical separation. Something earthwise has separated them. So there's physical separation. There's can't, right? And there's won't. That's called behavioral isolation. Birds are always pretty good examples for stuff like this, just because they're real picky. Especially with things like mating songs, or in some birds' cases, dances. You ever seen the Birds of Paradise? This ridiculous dancing, like to get a mate, the males will just do ridiculous things, and if it's not quite right, she's just like,
I remember back in like 7th grade, we watched like the geographic documentary or whatever.
Sure. Yep.
And then there was like this blackbird, and it'd go like up and down.
Yeah, that's it.
Oh,
I did. Yeah. That's really kind of match. I wish I had that on. Yeah, and if it's not quite right, she's just like, and so imagine a flock of birds that's been split into two populations. They're evolving independently now. And if that dance in this group changes at all, suddenly the ones in this group are not going to be into it with this group, right? Like they're not going to mate anymore. Two species. That's behavioral isolation. The other thing that can happen is that they can change in timing of things, and it doesn't have to just be nocturnal versus diurnal. That certainly works. If you know, if there's predators out during the daytime for this group, and they slowly start to evolve to where they're only active at night, and this group's still active in the day, they're not going to see each other anymore, right? That's called temporal isolation. Temporal just means having to do with time. It can be mating seasons not overlapping anymore. Okay. No, and she's out for, okay. Gotcha. Nope. Okay, fine. So think of it as like, you know, can't get to each other, won't interact with each other, and don't even see each other because of the timing. Questions? Okay, so back to Friday, when we talked about directional selection, stabilizing selection, and disruptive selection. The activity I have for you today goes with that. It is a graphing activity, so you'll have to kind of dust off your graphing skills. You're going to be looking at snakes over a period of time and the changes that happen. All right, this takes just a little bit of explanation because what you've got is 3 different times. You've got 3 different years that they're recording the lengths of these snakes. Okay, so what you're going to be doing is making what would normally be a bell curve, right? It'll be. So the main thing I want to make sure is that you understand that you're kind of programmed to put time on this axis, right? This is always time, not this time. Your times, the years, 1980, 84, and 88, those are going to be 3 different graphs on the same set of axes. So what you're basically going to be doing is saying, okay, in 1980, you know, here's length of snakes, and here's the number of snakes at each length. Okay, you know, we should see something probably like a bell curve. It won't be perfect. Okay, so like you're going to need a sort of a key, like maybe this is 1980, this is 1984, and then you know this is 1988, something like that, and you'll have 3 different graphs where you know maybe there's this here, and then like that, right? So you'll have 3 different snapshots of the snake population at 3 different years. Does that make sense? Get it? Okay, ask me if you have questions. Don't forget the box. You see this box over to the right that says type of selection and summarize what happened to the snakes? Don't miss that. That's important. Hazen.
For the summarize what happened to the snakes.
Yeah.
If they get longer, I'm gonna be like someone took the Play-Doh.
Okay.
Would that count as an answer?
That is an answer.
That's definitely correct.
I can't tell you that because this is homework.